The next speaker is V. Ramaswamy, and he is the director of GFDL, which is Geophysical Fluid Dynamics Laboratory in Princeton. And his title is Anthropogenic Species and Climate, Diagnosing the Past and Modeling of the 21st Century Climate Change.
Okay, good afternoon. It's a real privilege for me to be here, to be invited by Jim, and at this very august and very prestigious event honoring Jagdish Shukla. I never heard his first name mentioned often, so I thought I should put it down. As has already been mentioned by Dennis earlier this morning, that Shukla has and continues to have a very long association, and a very affectionate one, I would say, with GFDL. Came there as a student and then as a postdoc, and he's continued his association ever since. And I think we at GFDL are very grateful for that very fond association, because he always brings with him lots of questions, lots and lots of questions. I doubt if he ever gets all the answers, but he does bring in all the questions. And what is amazing is he's captivated successive generations at GFDL. I certainly wasn't there when he came as a visiting scientist, but his ideas and thoughts reverberate around GFDL a heck of a lot. One aspect of Shukla's very infectious enthusiasm, and an inspiring one at that, is his work in India. I think there are a lot of colleagues here who have connections with India and have past links with India. I think they can all testify to how he actually worked, sometimes even uphill against the system, to get things done in India. Starting with, you all have read about this, the biography in the booklet about his work in the village, in the Balia village in northern India, a very impoverished district, and his work in setting up the college. And I think a lot of things are not mentioned, like his work in inspiring young girls and women to go into sciences. And then his work in setting up the medium-range weather forecasting center in New Delhi and procuring a computer for them. I mean, this was all done in the 80s and 90s when it was very difficult to get things done in India. And here he was, almost a single individual, moving mountains to get things done. So I think this is all really a tribute to what others have mentioned about his activities in the international scene. I personally remember the time spent with him on the JSC, Joint Scientific Committee of the World Climate Research Program, and there was scarcely a day at any of these meetings when Shukla's things were not discussed from morning till evening. It always, kept coming up and up again and again. COPES was a fantastic example, because there were so many hot debates and discussions that surrounded this. I think very fond memories of that. Now, for this talk, for this time slot, I can pick up and talk about a lot of things happening at GFDL along actually Shukla's pet lines, like seasonal predictions, the increase of resolution of models, the increase of complexity, capturing the realism with more accuracy. But instead, I'm going to choose to talk about something which I think hasn't been touched upon, and that is a factor which is just as important as other factors that have already been mentioned in terms of climate in the 21st century. And that concerns short-lived species, and I've listed my collaborators, who are more than collaborators. They actually did all the work: Yiming, Elissa Ocko, and Dan Schwarzkopf. So I'm going to begin with an animation which purports to capture the movement of aerosols, and that's going to be the subject of the talk, captured using an atmospheric model nudged to NCEP reanalysis, and it's a 50-kilometer grid. So let this start, and this actually is for the 2012. It starts somewhere around October of 2012, and there are two events that happened, which you'll sort of see here. Let me see. I have to get this back. Come on. Let me start it, then maybe something will happen. So it's supposed to show two events. One was a dust storm going off Midwest. This starts in sometime in October. So you'll see a big blob of dust coming, which is brown in color, coming off the Midwest, Nebraska, going all the way down to the East Coast. There it goes. And then a few days later, Hurricane Sandy will be spinning up and going along the coast and then making its famous leftward turn. And the other things on this diagram, there it goes, the Hurricane Sandy. And the other things on this diagram are, the green color is essentially carbonaceous aerosols, organic carbon and soot. And then sulfate is in white and sea salt is in blue. And you can actually see all the circulation, major circulation features in the global atmosphere through these short-lived tracers, which are aerosols. And these include both natural and anthropogenic emissions. And so it's a model which is actually capturing from the emissions to the transport to the removal process of the various aerosols. And this is kind of the grid that you're working on, 50 kilometers. So this is actually going to be the grid for the next generation model. Now, I did something I shouldn't have done. How do I get back? Oh, okay. Now, I want to advance this. Okay. So, I'm going to skip the slide. So I want to talk about this slide now, which is the famous IPCC forcing of climate diagram. And there are two things in particular, the only two things I want you to notice. One is this relative forcing being positive for the well-mixed greenhouse gases. So that's well known. It's coming along from almost time immemorial. So that is well accepted. The thing that is the major issue is the aerosol forcing. And there are two components. One is the aerosol forcing in skies without clouds. And that, if you see, consists of a positive bar and a negative portion. The positive is essentially soot aerosols, which are absorbing, and the negative is the sulfate and organic aerosols, which are mostly reflecting. So you have this nuance with aerosols, which is not there with greenhouse gases, where some of the components are actually absorbers of radiation, some are not. And then, of course, the major problem is this aerosol-cloud interaction, where it is negative, according to the consensus assessment, but has a large uncertainty bar, which plagues actually both the past and the present understanding of the climate system, both the 20th century as well as the 21st century. So then I lay down the issue here, which is the effect of these emissions on the 20th century, and most often the temperature change is talked about, and that's, I think, well understood, well in grasp in terms of what aerosols do to the temperature related to greenhouse gases. But here I'm going to focus almost entirely on the hydrologic cycle changes. And then in particular, contrasting the effects of the greenhouse gas and the aerosol emissions on the hydrologic cycle. And then in particular, since from the previous diagram, we saw that some aerosols go in one direction, others go in other directions. What is the effect of the sulfate versus black carbon? And then implications for 21st century based on what we are diagnosing for the 20th century. So for these, the results I'm going to show, these are simulations with the climate model CM3, which had this resolution, 100-kilometer atmosphere, 250-kilometer ocean, and was the one used in IPCC AR5. And what I'm going to sort of resort to is simulations performed for a combination of forcings, which has which at least is the idea of unearthing what the different forcings may have done. The model that was used, this is just a rough description, cube sphere dynamical core, and is designed to address chemistry climate feedbacks, both in the stratosphere and the troposphere, and included aerosol cloud interactions in a prognostic way. And then the forcings these are the forcings given to the model: solar radiation, volcanic aerosols, the well-mixed greenhouse gases, and then the other greenhouse gases, methane, nitrous oxide, ozone-depleting substances, and then short-lived emissions, which includes aerosols. And then the model had a atmospheric chemistry module to go along with the atmospheric dynamics and the ocean model, and then coupled to a land model. So here is, first of all, the time series of the anomalies from this model. And the black line is the observed anomalies, so that's the CRU anomalies. And then, so here is the thing where you can actually ask the question of what does the result look like if the Earth were, in the 20th century, were forced entirely by greenhouse gases. Well, that's what you'd get if it had been forced entirely by greenhouse gases in the model. You can ask the same question about natural aerosols, solar and volcano. That's sort of the green curve with large dips with the volcanic emissions occur in the model. And then tropospheric aerosols represented by this brownish-looking curve. And really the contrast between this, the red line and the brown line, is the one that determines how the model, which is the all forcing result, combination of all forcings, evolves. So you can see that the model actually underestimates the warming. It does capture the last 20, 30 years of sharp rise in warming, but it does underestimate. But the bottom line is that the net result is the combination of these two opposite sign forcing. So that's the temperature. And this just captures it in a sort of a bar diagram form, where this is the change if it was only due to greenhouse gas and ozone, and this is due to aerosol, and the crosses represent just different members of the ensemble. And so that's the all force is the net result. It's not slightly nonlinear, but nevertheless, this bar is taller than this one. And that's kind of what happens in most of the models in terms of the temperature response. And this is the last 50 years of the 20th century. Precipitation, looking at in the same manner. First of all, of course, precipitation, it's highly noisy, and so trying to get statistical significance is a difficult task. But the purpose of the talk here is to really compare these two guys. And you can see that unlike the temperature case where the greenhouse gas was overwhelmingly bigger than the aerosol response, here it's actually comparable. And that kind of has a big effect in terms of, let's say, attribution to precipitation, if indeed we were able to do detection attribution of precipitation cleanly, as we can do in the case of temperature. And looking at not just those are the global means in the previous slides, but if you look at different regions, you can see a similar result. This is the same diagram as you saw in the previous slide. So you see the greenhouse gas and the aerosol bar roughly comparable, but opposite in sign. Europe, it's sort of aerosol is a little bit more. North America has a similar picture to the global. Asia is where the largest difference occurs between these two, with the aerosol actually leading in terms of magnitude. So hydrologic cycle effects become pretty important in terms of aerosol relative to the greenhouse gases. You can analyze this in terms of the surface flux change. This is global annual mean. And so if you look at the greenhouse gases, this is a very classic effect of greenhouse gases that at the surface, you gain energy from the long wave radiation, net long wave radiation arriving at the surface, and then that is balanced, these are all global annual means, and that's balanced by the latent heat release from the surface, which is lost from the surface. Aerosol, you have the biggest bar in the short wave reduction, and that's kind of the key thing here, the short wave reduction, which then is balanced by a net loss of latent heat, or the surface is gaining latent heat because there's not much evaporation going on because of reduction in short wave, or at least that's a major term. And then the all force is actually reflecting the aerosol reduction in short wave. It does have the long wave increase at the surface, but the latent heat effect is swinging more towards the aerosol, at least in the context of this particular model. Now, one of the things that does happen in this model, which was noticeable when you saw the temperature decrease in the first slide, is that the aerosol forcing was probably too large, and we suspect that's because of the aerosol cloud interaction forcing. But we can go back to an earlier model. This was actually a model used in IPCC AR4, which did not have the indirect effect. It has slightly different emissions of sulfate and carbonaceous aerosols, but so that model doesn't have the aerosol cloud interaction effect, which is a big effect. But even in this model, if you look at the global mean precip change, again you see a balance occurring between the aerosol and the greenhouse gases, and again a larger effect in Asia and so on. So this is the conundrum that the sulfate and carbon emissions together have actually conspired to give a very large effect on the hydrologic cycle. Now, another facet that comes out when you start looking at the aerosol versus greenhouse gases is their distribution, and therefore their forcing. So this is now a diagram showing the annual burdens of sulfate and black carbon. So the sulfate is on the right-hand side, black carbon on the left-hand side. And the key thing is that they are dominant in the northern hemisphere. So they are more in the northern hemisphere than the southern hemisphere, creating an interhemispheric asymmetry. And the forcing roughly translates in a linear manner to this, so the forcing is also more in the northern hemisphere, positive for black carbon, negative for sulfate, but very little in the southern hemisphere. And this is to be contrasted with the greenhouse gas forcing, which is not drawn here, but it will be pretty uniform in both the northern and southern hemisphere. And there's a significance to this intrahemispheric forcing asymmetry, which is kind of very similar to other problems that have been encountered, like the last glacial maximum when ice sheets are only in the northern hemisphere, or afforestation ideas where the land albedo changes are only in the northern hemisphere. And the net result is, apologize for the smallness of these slides, but if you look at these, just this middle panel, if you look at the sulfate, and what is plotted is precipitation in the sort of curved line plot, and then the color plots are vertical velocities. So because the sulfate is reducing the radiation of the surface, you have a reduction in the diabatic heating, and that's dropping the vertical velocity. But because of the fact that there's an intrahemispheric asymmetry, you have this response where there's a decrease in precipitation just approximately south of the equator, and an increase in the northern side, in the southern side of the equator, a decrease in the northern side. And black carbon, exactly the opposite, although there's a slightly different reasoning because black carbon effects are included in absorption of the atmosphere, but the net effect is just the opposite of the sulfate. Now together, when you consider them together, they actually do offset each other, and this is to be compared to the greenhouse gas, very sort of canonical signature of the greenhouse gas where there's a peak near the equator in terms of precipitation. And this is, there's a lot of studies which have actually explored this, and there's a very easy explanations for this. So I'll skip through this. The other factor associated with the aerosols is the total heat transport. And here, positive means going poleward. So for greenhouse gases, the heat transport is towards either pole, whereas for sulfate, which is a blue curve here, you have a heat transport towards the northern pole. And so it's totally different from greenhouse gases. Black carbon is exactly the opposite of sulfate. So amongst the aerosol species, you tend to have this cancellation amongst themselves, and then together they have this opposite reaction to what greenhouse gases do. So 21st century, the two important things are envisaged in almost every scenario. Greenhouse gas increases, aerosol decreases. And first of all, I'll do a plot of the particulate concentration currently in Beijing and Delhi. So this is a scatter plot, and this is hazardous. So here you don't want particulates to be rise in this regime, and this is why aerosols are going to go down in the atmosphere, almost certainly in the 21st century, because it's very. Just interpret this curve as saying that in Delhi, 20% of the time it's hazardous. The atmosphere is hazardous for health, according to World Health Organization definitions. Whereas in Beijing, it's about less than 10%. But the bottom line is both Delhi and Beijing, by sort of inference, India and China, do have to worry about the particulates, so they are going to go down. So what happens when aerosols go down is, on the temperature scale, you're going to have, of course, an increase in temperature relative to today because of both greenhouse gas increase and aerosol decrease. And here, the difference is due to the aerosols. The hydrologic cycle is the more interesting because, again, the current model, this is how greenhouse gas alone would have taken the precipitation. The aerosol brought this system down, and then once the aerosols are gone, it's like a spring released, and you go down up. And the most important difference is, in this model at least, is the East Asian summertime precipitation. So let me, you can sort of see that in the latent heat, in the sort of change in the global surface heat flux, both the short wave changes, it increases because aerosols have gone out, greenhouse gas have increased, so you have more long wave down to the surface, which means a larger latent heat effect. So with that, I will come to my summary, which is that the dominant effect in terms of the hydrologic cycle has been by aerosols, electric greenhouse gases. And then sulfate and black carbon emissions, besides kind of offsetting each other, are also having cross-equatorial precipitation effects, which all these things would have to be reversed if the aerosols are going out of the atmosphere. And so the implications for the 21st century is the drawdown of the aerosols, which would then offer a reversal from the 20th century effect. But it also depends on how much sulfate and soot are going out of the atmosphere. So this is a plug for how important the short-lived species are in terms of determining the climate in the 21st century. And again, I wish to thank Shukla for this opportunity and Kindred for this opportunity, and also for very tough questions he's asked me before on aerosols and climate in past meetings. Thank you.